Hi there. Welcome back to your Fundamentals of Human Physiology and Homeostasis. In part two, we're going to discuss oxygen, its relationship with ATP, and how they help in homeostasis. So our objectives for this part of our lecture is going to be describe oxidation reduction reactions and explain the role of ATP in metabolism. We want to be able to state what the products of cellular respiration are and how they dispose, or how our body disposes of them. We'll define hypoxia, ischemia, and infarction. We'll explain the importance of hemoglobin, myoglobin, talk about oxygen debt and lactic acid. Finally, and we'll describe some different types of pain. We'll talk about somatic, visceral, referred, and phantom pain. We'll start all this off with introducing the idea of oxidation reduction reactions, oftentimes just shortened to redox reactions. And what a redox reaction is the transfer of electrons from one molecule to another. Oftentimes, this is in the form of transferring or moving around hydrogen ions. Okay, this is the type of reaction that happens in aerobic metabolism or metabolism with oxygen. Okay, our oxidation is going to be losing electrons, and reduction will be gaining electrons. Great way to remember this is the oil rig, OIL. Oxidation is loss, that's oil. RIG, reduction is gain, that's rig. So oil rig, oxidation reduction reactions, or redox, just the transferring of those electrons from one molecule to the other. And we see this in metabolism when we have oxygen present. Our glucose is going to be oxidized to carbon dioxide. Our oxygen is actually going to be reduced to water. And this process will create energy, or ATP. Let's take a little bit of a better look at this. And I want you to imagine redox reactions like a seesaw. If one thing is being reduced, then something else in turn must be oxidized. So in our metabolism or aerobic metabolism, we have glucose and we have the presence of oxygen. In this glucose oxidation, our cells are going to break down glucose in a series of these redox reactions. And our oxygen is actually going to be reduced, meaning it's going to be our final electron acceptor. And when this happens, we're going to create H2O, or water. We're going to create carbon dioxide. And then we're going to create a ton of energy, right? This is going to cause energy release from these reactions, and it's captured in ATP, or the body's energy currency. And this aerobic metabolism is going to create 38 ATP, lots and lots of energy. Not only do we create lots of energy, but we create other byproducts, our water and our carbon dioxide, that are easily managed by our body. Water can be reused or just excreted by the kidneys. That carbon dioxide can actually just be easily breathed off by the lungs, leaving us just that ATP, tons of ATP to use in our body. Now, when we have a patient who is hypoxic or lacking oxygen, we struggle to complete these redox reactions efficiently, and that leads us to do anaerobic metabolism. That anaerobic metabolism makes some not so great products, including lactic acid, and causes lactic acid buildup. Without that oxygen, we end up with very little ATP, only 2 ATP, and that lactic acid buildup. Not a great situation, and why it's so important that when our patient is lacking oxygen, we are able to give them supplemental oxygen. This helps restore normal cellular respiration by providing oxygen to be that final electron receptor, to allow for those redox reactions to happen and for us to go back to aerobic metabolism. Now, if oxygen's so important, then our body must have a way to not only move it around and get it to all of our tissues, but to also, in some ways, store it so we have it available when we need it. And we do that through what we call oxygen binding proteins. Okay, two major ones in our body, hemoglobin and myoglobin. Now, if we kind of look at that word hemo, that sounds familiar, right? That's usually has to do with the blood. And that's because hemoglobin can be found in the blood. It's actually found in our red blood cells, and it looks a little bit like this. With these four different parts, we are able to transport four oxygen molecules in that hemoglobin, and that makes hemoglobin our transporter. This is what brings oxygen to all of our tissues throughout the body. Then we have myoglobin. Now, that word also might sound familiar. Myo means muscle. That's because myoglobin is found in the muscles. And we want to think of myoglobin kind of like a storage tank. It's like our oxygen reserves. It's where we can hold on to one oxygen per myoglobin to use when needed, right? To use if we need oxygen immediately. We don't have time to wait for oxygen to come through the transport system or through hemoglobin. And we really want to make sure that we are filling up our hemoglobin with oxygen, but we also are filling up our myoglobin with oxygen, that both the transporter and the storage tank are full of oxygen. When our patient lacks oxygen, when they don't have enough oxygen in these oxygen binding proteins, we're going to say that that patient is hypoxic. So hypoxia is the lack of adequate oxygen supply. So when we don't have enough oxygen to fill up oxygen binding proteins. Now, oftentimes this can be confused or mixed up a little bit with the idea of ischemia, where oxygen is lacking oxygen, right? Our hypoxia does not have enough oxygen. Ischemia is when we don't have enough flow. So this is reduced or blocked blood flow. Has nothing to do with the oxygen levels in the blood, has everything to do with can the blood get to the tissues. So ischemia is when we have reduced or blocked blood flow. And that finally can bring us to infarction. So if ischemia goes on long enough, we'll end up seeing tissue death from the lack of blood flow. These are things that we see in myocardial infarctions, right? Or heart attacks. We can see them in strokes. We can even see them in the lungs with our pulmonary embolisms. That lack of oxygen can eventually cause tissue death if let long enough. So a way to kind of help us differentiate and understand a little bit better is to think about our tissues kind of like a burning building. And we're going to use this burning building analogy to understand how these three terms kind of differentiate. Okay, so if we have our burning building, that's like our tissue in need of oxygen. Oxygen is going to be water. And we want to make sure that we prevent the building from burning down or from dying, right? Tissue death. So if we have this burning building, hypoxia is going to be the firefighters are there, they arrive, but the hoses are even working, but there's no water. The water pressure is much too low. And the key idea here is that water or oxygen is still being delivered. It's just not enough. Right? We're getting it there. We're getting the blood. We're getting the firefighters there. We just don't have enough water to put out that fire. On the other hand, ischemia is when the water supply is fine, the trucks are filled with water, the water hydrant's working, we have the oxygen available, but the fire truck is stuck in traffic. It's locked on a road. The fire trucks can't reach the building. And the key idea here is that the problem isn't with oxygen. It isn't that we don't have water. It's that there's a lack of blood flow, an inability to get the firefighters there. in order to deliver it. And finally, that brings us to infarction. If the firefighters never arrive, if that blood flow never arrives, the fire will just keep burning until the building collapses. The tissue will die. So if ischemia isn't fixed, the tissue dies permanently. So when we think about what that looks like in our patients' bodies, think about the heart muscle. If the heart muscle doesn't get enough oxygen, patients will experience angina or chest pain. Think about muscles. When muscles don't receive enough oxygen, they end up switching over from aerobic metabolism to anaerobic metabolism, and that will lead to lactic acid buildup. This will change or lower the pH levels and activate our pain receptors, causing a deep or aching or cramping pain, right? The lack of oxygen can lead to pain, but how pain is felt in the body really depends on where we are seeing it, where that pain is originating from. So somatic pain, this is a really well localized type of pain, often described as sharp or throbbing pain. Think of this kind of like shutting your hand in a door. You know that pain. On the other hand, we have visceral pain. Now, this is oftentimes very poorly localized, hard to pinpoint where it's coming from in the body, described as like a dull or cramping pain, kind of like that random stomach ache you get and you can't really identify. So somatic pain, well localized, sharp throbbing pain. Oftentimes, this is going to be associated with our muscles or solid organs in the body. Visceral pain, that poorly localized, dull or cramping pain, this is going to be more commonly things like the stomach or the intestines, our hollow organs in the body. Now, two different kinds of pain that we are going to also want to discuss. Referred pain. This is pain that radiates to a different location. So it's pain that originates somewhere, but you feel it in a different place in the body. And this last one, maybe the most strange of all the pains, is phantom pain. This is pain in a body part that is no longer there. So oftentimes, pain in a body part that has been amputated. A patient who reports pain in their left foot, but they had a left leg amputation at the knee and no longer have a left foot. Their brain is getting the signal or telling it like, hey, your foot hurts, but there's no foot to be had. That's phantom pain. Different types of pain for different places in the body. Different patients will report different feelings, but we know that pain tells us oftentimes something is wrong. Sometimes that thing that's wrong is lack of oxygen. That is it for part 2 of our fundamentals of human physiology and homeostasis. Just one more part, we'll do a part 3, and we're going to talk about homeostasis and water.